All right, this is the Turbine Lab, and we're going to get started here. So these are the turbine controls. Unfortunately, I wish I could have taken y'all in there to see this thing. It's pretty impressive, actually. NMSU's about 4 years ago now, we spent right at $800,000 to upgrade our controls. This turbine and the controls were put in 1996, and it's a Caterpillar company called Solar. Was when it was put in, and they came in, and it was about a $20 million project to put this in back in 1996, and then in, I guess it was 2016, we paid another, I think it was about $800,000 to get the controls upgraded, because Solar was not going to support the 96 controls, so we had to upgrade the thing. And this is all computer generated, all computer driven. The computer controls everything on this turbine. And if you look at that center console there, this is an Allen Bradley control, and this tells us everything that's going on with the turbine, what the temperature is, what the exhaust temperature is, tells us how the bearings are working, if everything is good, what the temperatures are. And if we have any kind of problem with this, anything that's out there on the turbine, then what happens is one of these, whichever one goes bad, temperature goes off our out of limits, it'll automatically shut the turbine down. So that's the fail safe. And that was one of the reasons why we decided to go ahead and put new control system on it, so that we wouldn't have to worry about it going offline due to or causing damage because it wouldn't, something happened inside and we didn't know it happened. So you got to keep the controls up, and it did cost us quite a bit to do it. Also on that panel, you'll see the operators over there can figure out exactly what's going on. Make sure that the generator is putting out exactly what we want. So you see it's putting out right about 4.2 megawatts when I took this picture, and the voltage is hovering around 4,200 volts, and we're putting out just a little over 600 amps on this thing at this time. And we have two circuits. We have 4 circuits on the main part of campus, and then 2 circuits that'll take this excess power down to Tortuga substation. You get a little more into it, you'll see that our frequency is pretty doggone close to 60 hertz, which is what it's supposed to be. And that the power factor is 0.9 lagging. We have our turbine controlled so that it will always be at 0.9 lagging, and that way we don't have to pay El Paso Electric a premium, even though your fees, your tuition went up 3% this last semester, or 3% in the fall is what it's going up. And so we monitor what we take from El Paso Electric, and we make sure that we never go below 0.9 lagging, otherwise El Paso Electric will charge us a lot of money. These 2 meters basically control, well, in the turbine video you saw that they had a field current. Well, this is the field current, and the voltage, the DC voltage and the DC field current that we put onto the rotating part of the turbine that sets up the rotating magnetic field that then imparts the power through Lorentz law, power, and Faraday's law, and puts it into the stator windings and sends the power out. So we're running right about, looks like about almost 2.5, 3 amps DC right here. It's about 2.75 is what it looks like. And then the voltage is what we, 2.75 amps DC. And so that's how much voltage we have coming off this thing to supply that. And this is automatic. As the turbine ramps up, we put more and more current into it, and we get more and more power out until we reach the maximum power, which this turbine is rated for 5 megawatts. And the only time I've ever seen it get to 5 megawatts was when it was minus 11 degrees outside. So pretty impressive machine. It's very well controlled. The guys at the central plant do a pretty good job of it. And those are the controls. And we get feedback from that. That feeds into our Niagara system and tells us what's going on. At the end of this little slideshow, I'm going to show you what happens when you don't sync in. Anyway, these are all the synchronous controls. So what happens is controls, LS, there we go, controls. What happens is when you want to bring a generator up and put it online, what you need to do, you can operate it two ways. You can operate it as that turbine only. But the problem with that is that if your turbine goes down, then you have no other power to resort to. So what we do is we also piggyback onto El Paso Electric. So El Paso Electric, if our turbine goes down, El Paso Electric will immediately pick up all that power that our turbine lost, if and only if our turbine is synced in to their system. And these are the controls to synchronize our turbine to their system. So you'll hear, if you decide to go into power, you'll hear something called an infinite bus. And an infinite bus is just that. If you look at El Paso Electric system, which is probably, golly, I don't know, I'm taking a guess here, what, 25,000 megawatts? So let's just say EPE is 25,000 megawatts. That's how big their system is. They make 25,000 megawatts and put it on the system, and everybody in El Paso in this region uses that power. Well, NMSU power is 4.5 megawatts. So EPE looks like an infinite bus to the New Mexico State University turbine. And what happens is if we try to put our turbine in parallel with El Paso Electric and we don't sync it in, we wouldn't have a turbine anymore. That thing would go through the roof of that building over there and it would be grenaded all over campus. So what you have is, a better explanation is, you have a big watermelon that's EPE, and you have a little tiny grape over here that's NMSU. And that big watermelon will crush that grape at any time, and that's exactly what will happen if you don't synchronize in. And there's two ways to do it. Our turbine actually has a automatic synchronizer. So when the waveforms and the frequency and all that stuff get into sync, then it'll automatically close in our breaker, our turbine breaker, onto the El Paso Electric system. or it will close in our EBT tiebreaker into the El Paso system. Depends on how we're operating the system. You can also do it manually. And that's what these two lights are for right here. Basically, one light is on El Paso Electric system, and one light is hooked up to our turbine. And when you're in sync, those lights will be nice and bright. So when you're in sync, you can go over and either hit the EBT breaker, close right here, and we also have a generator breaker switch outside. And so you can close it manually. And what will happen is you'll see these lights, they'll go dim and go off, and then they'll start coming on and get brighter and brighter and brighter, and then they'll start dimming again. And when they're nice and bright, then you close in your breaker and you're synced in with El Paso Electric. So infinite bus, EPE, little tiny bus, New Mexico State University. Again, if you don't sync it in, you have problems. Our system also has our one-line diagram, which unfortunately I didn't get to show y'all, has a lot of cautions, cautionary exclamation marks on our map where we could tie into El Paso Electric if and only if our turbine is synced in. But if it's not synced in, then we have those cautionary things that says basically call the central plant and make sure that the turbine is synced in with El Paso Electric. Otherwise, that switch will jump off the ground, and so will our turbine. Okay, here's a picture. Basically, this is a cutaway of the turbine that we have. If you remember, it compresses the air up in this area right here, and then it injects the fuel right in this area, and the exhaust gas goes out that way. On this, it's a little different in that this shaft right here also turns a generator. And right here, you'll see right here, this little hole right here, that's where you can mount an AC supplied motor that'll get this turbine almost to synchronous speed. For this turbine, synchronous speed is 1800 RPM. I was wrong. I finally found a picture of the nameplate data, and I thought it's actually 1800 RPM, revolutions per minute. I thought it was 36, but it's not. We have a very sophisticated control system that puts fuel in there. I'm sure everybody's heard about 3D printing. You know, when did 3D printing come along? Well, I can tell you that these guys, we have 3D printed natural gas nozzles that inject natural gas into that turbine, and they've been making those things since the 80s. So 3D printing's been around a lot longer than I ever thought it had been. But that's a cutaway picture of our turbine. Have a transmission. Basically, this motor fits in there, turns those gears, cranks up the motor. The turbine, it starts spinning right around just less than probably around 1725 RPM, non-synchronous speed. And then they start upping the field current. And once they get a field current on there, then that thing comes up to the other 75 RPM and picks up and goes on to synchronous speed. And I can't ask if there's any questions because there's nobody listening to me yet. All right, so here's our turbine right here. This is the inside of the turbine. Right behind here is that jet engine. That's where the jet engine is. Like I say, it gets really hot. We use the exhaust gas from the jet engine. And we use the exhaust gas to make steam. until 2014. Until 2014, we had a lot of excess steam or a lot of excess exhaust gas going into the atmosphere. And in 2014, we actually, and the reason that was, is in the summer, we don't use very much steam to make hot water. So we don't need steam to make hot water. You know, it's hot enough as it is. So in 2014, we put a steam-driven chiller in. So a chiller basically makes chill water. And that chill water, we have a 3 million gallon tank over in that parking lot on the south side of that building, the central plant. We have a 3 million gallon water tank, and we put chill water down in there and we store it and keep it nice and cool. Down at the bottom, it's about 40, 42 degrees. Up at the top, it's about 55 degrees. And so in the summer, what we do with that steam-driven chiller is we make lots of steam, and we send that steam over to that steam-driven chiller, and it makes chill water for us to keep our storage tank cold. One of the things that you'll find when you get into industry, depending on where you go and what you do, is you always have the I'll rub your back or I'll scratch your back if you scratch mine. So one of the reasons that we get such a good deal from the city of Las Cruces is we buy a lot of natural gas in the summer. Well, so that means that El Paso Electric, as long as we run our generator all year, which we do, then City of Las Cruces knows that we're going to be using that, and it's a lot of natural gas, let me tell you. They know we're going to be using a lot of natural gas, so they can get better prices, because typically the only time you use natural gas in this town is in the winter. There might be natural gas hot water heaters, but you're not using them. You know, that's not a big demand for those. So in the summer, you'd have natural gas water heaters. They would be working year round, but your heating in your house or your apartment won't be working year round. So because we buy such large amounts, summer, winter, fall, spring, City of Las Cruces gets a really good deal on natural gas, and so we get a really good deal on natural gas. So it helps everybody in town get a much better rate on their natural gas. Here are the natural gas controls that feed into the generator. This is the natural gas. We get natural gas at 150 psi, and we drop it down to about 120 psi and put it in the turbine. And it, like I say, it's all explosion proof. Everything is, once those doors close, any kind of fire or anything like that will be picked up by an infrared eye and shuts everything down, so we don't have too much damage. But these are the natural gas controls that inject natural gas into that turbine. Very sophisticated. So you can look in here. I know y'all don't know what I'm talking about right here, but all these fittings right here are all explosion proof fittings. Vapor tight, all that good stuff, so that if something ever got loose in there, it wouldn't go anywhere and blow the thing up. All right, this is the transmission part of it. Right here on this side over here is where that motor goes that I showed you in the drawings. This is where the turbine is over here. The actual jet engine's back over here. In fact, you can see that in that last, where are we? Here we are. You can see a little bit of that in that last paragraph right here. See, here it is right here. There's the coupling that couples the turbine to the generator. So Not a whole lot to see there, but just interesting nonetheless. And then I was telling you about the motor that turns the turbine and gets it close to synchronous speed. This is a three-phase motor, runs about 1725 RPM. They start injecting current onto the rotating mass of the generator, the rotor, the windings of the rotor, and then once they start injecting it, and then once they get everything going, then all they have to do is put that current on there, and it sets up that magnetic field, and the turbine picks up that last 75 RPM and turns at synchronous speed, which in this case, again, 1800 RPM. This motor is fed with a 1950s generator, so if the turbine goes off and we also lose El Paso Electric, then we can turn that generator on and it will start the turbine and get power back onto our central plant and back onto the middle part of campus again. Let's see, can we see it? Can we see it? Yeah. Right here is the generator. The generator starts, the generator part of the turbine starts right there, and it goes about another, I'd say probably 10 feet. And this is the back side of the generator. And this is where we have two things on here. We put the DC current in onto a set of slip rings, and then we also have our voltage control. Voltage regulator. And this is where we put the field current onto the slip rings. So we put the field current onto the slip rings, and which is part of the turning mechanism. It's the rotor part, and then that current goes into those windings on the rotor. This is a 4-pole motor, goes into the windings on the motor, and that constant rotating magnetic field injects a time-varying magnetic field onto the windings of the stator, and you get AC power out. Once again, all the explosion-proof fittings on this stuff to make it work, because they don't want to have any type of electrical spark in there or anything like that. So that's the generator. And then here's the shaft I was telling you about where it broke. It actually broke, looks like it got hit 3 times. Once right there, and then the final shear was the rest of it right here. But this is off a water turbine. They turn very slow, like a, I don't know, what, 12 pole, 48, probably a 48 pole motor, something that turns real slow. And what these guys were doing, it was put in back in the 60s, and they'd never had a control system, and they never had somebody come in and tell them that, hey, you got to sync your system to the power system, otherwise you're going to have problems. And so over the years, they've had to replace generators because they weren't syncing in. They had about 4 10 megawatt generators that they ran all the time, and then they had 2 backups. And this